The chain rule is used to differentiate the composition of functions. So let's begin by reviewing what the composition of two functions looks like. From our notes, we define the composition of two functions f and g. So let's look at an example. Suppose f of x is equal to x squared plus x and g of x is equal to 3x plus 2. Let's find f composed with g and g composed with f. So first let's remember what f composed with g, what that means. So we use this notation, but what this means is we take the g function, and what we're doing is we're plugging the g function inside of f. So we're taking f of the g function, which is 3x plus 2. So we're replacing all the x's in the f function with 3x plus 2. So f of x is x squared plus x. So we're replacing the x's with 3x plus 2. So here's a 3x plus 2 squared plus 3x plus 2. Now simplify. So multiply out the 3x plus 2 squared, which gives us 9x squared plus 12x plus 4, and then we have the plus 3x plus 2. Combine like terms, combine the 12x and the 3x, and we get 9x squared plus 15x plus 6. Now, doing g composed with f. So we're taking and we're plugging the f of x function into g. So we're taking g of f of x, which is x squared plus x. So in the g function, what we're going to be doing is replacing all the x's with an x squared plus x. So we've got 3 times x squared plus x plus the 2. Simplifying by distributing the 3x squared plus 3x plus 2. Now I want to point out that g composed with f is not the same as f composed with g. Notice we get two different answers. And in general, they are not equal. The only time f composed with g equals g composed with f are when f and g are inverse functions of one another. Here's another example from your notes. We're looking at the function f of x equal to x plus 3 and g of x equals square root of x. We want to find the composition f composed with g and also g composed with f. So beginning with f composed with g, we're taking the g function and we're plugging g of x inside f. So g of x function is square root of x. So we're plugging square root of x into all the x's of f of x. So we're replacing the x in f of x with square root of x. So we get square root of x plus 3, and it's already simplified. So that is our composition function f composed with g. Now let's find g composed with f. So we're taking the f of x function and we're plugging it into g. That's what this means, g composed with f. So f of x is x plus 3. So we're taking x plus 3 and we're plugging it into g. So we're replacing the x in square root of x with an x plus 3. So our composition function then is the square root of x plus 3. Notice how once again f composed with g does not equal g composed with f. So now that we've reviewed composition of functions, we now have the chain rule that's used to take the derivative of the composition of functions. The derivative of f composed with g is defined by f prime of g of x times g prime of x. One way to think about this is we're taking the derivative of the outside function f times the derivative of the inside function. Now we've seen the extended power rule. The extended power rule is a special case of the chain rule. Now it turns out that the chain rule can appear in another form, and we'll see it used in another form. And that form looks like, suppose we have y equal to the function f of u, and u is equal to g of x. Then the derivative dy dx is equal to dy du times du dx. Even though this form looks different, we're still accomplishing the same thing. We're still taking f composed with g, and we want to take the derivative of f composed with g. But when we create the composition of functions, y then is defined in terms of x. So we take the derivative of the outside function, dy du, times the derivative of the inside function, which is u, or g of x. So then we're taking the derivative of u with respect to x. So let's look at an example of using the chain rule. We want to end up finding dy dx, but along the way we need to find dy du and also du dx. So our function here, y, is defined to be the square root of u, and u is equal to x squared minus 3. So we'll begin by finding dy du. I can rewrite y, which is the square root of u, as u to the 1/2 power. That way, when we take the derivative, we can use the power rule. So bringing the exponent out in front, we have 1/2 u, and then subtracting 1 from the exponent to the negative 1/2. Next, let's find du dx. So taking the derivative of u with respect to x, bringing the 2 out in front, we have a 2x as the derivative. Next, to find dy dx, we need to define y in terms of x. Y is equal to the square root of u, but we're going to replace u with an x squared minus 3, since u is equal to x squared minus 3. So now we've defined y in terms of x. So let's take the derivative dy dx. So using the chain rule, dy dx is equal to dy du. We already found dy du. It's 1/2 u to the negative 1/2. So we have 1/2. Now we're going to replace u with x squared minus 3 to the negative 1/2. So there's dy du. Now we're multiplying it by du dx. We found du dx to be a 2x. So now let's simplify. The 1/2 and 2 cancel, so we're left with x over the square root of x squared minus 3. In this example, let's find the equation for the tangent line to the graph of y equals the quantity 3 cubed minus 2x to the 4th at the point 1, 1. We've done problems like this before, but now in order to take the derivative of this function to find the slope of the tangent line, we need to use the chain rule. Now recall, when we're finding an equation of a tangent line, what we're looking for is something of the form y equals mx plus b. So we need a slope m and we need a y-intercept b. So in order to find the slope, we need to take the derivative of the equation given to us. Recall that the derivative gives us the slope of the tangent line. Now when we take the derivative, we have to use the chain rule. And in order to see why the chain rule is necessary, I've rewritten the function given to us, and I want you to break this into an outside function and an inside function. We can view the outside function as the function f of x equal to x to the 4th, some quantity raised to the 4th power. And then the inside function we can view as g of x equal to x cubed minus 2x. So we have an inside function, g of x, and then it's being raised to the 4th power. So now when we take the derivative of f prime of x, using the chain rule, we're going to take the derivative of the outside function. So bring the 4 out in front, kind of mentally block out that inside function. Subtract 1 from the exponent. So there's the derivative of the outside function. Now we need to multiply by the derivative of the inside function. So we're multiplying by 3x squared minus 2. So that's the derivative of the inside function, which is the x cubed minus 2x. Simplify a little bit and we have a 12x squared minus 8 times x cubed minus 2x quantity cubed. Now we need to know the slope at the point 1, 1. We need the slope for the tangent line at 1, 1. So we need to plug 1 into the derivative. So we have 12 times 1 squared minus 8 times a 1 cubed minus 2 times 1 cubed, which simplifies to give us a negative 4. So now our equation of our tangent line looks like y equals a negative 4x plus b. We still need our y-intercept, so we can plug our point in. Our point was 1, 1, so plugging 1 in for y and 1 in for x, we can then solve for b. So adding 4 to both sides, we get that b is equal to 5. So then our equation looks like y equals a negative 4x plus 5. And that is our equation of our tangent line to the function given at the point 1, 1. I want to take a moment to give you a visualization of what we just found by using our graphing calculator. So I'm going to hit y equals, and under y1 type in the function given to us. So x cubed minus 2x raised to the 4th power. Next I'm going to hit graph, so it graphs the function for us. Now what I'd like to do is be able to zoom in on this function a little bit. If I check my windows, the standard viewing window is a negative 10 to a positive 10 along the x-axis, and also a negative 10 to positive 10 along the y. I want to zoom in, so I'm going to hit zoom and then option 2 or arrow down to 2 and hit enter. Now my cursor is right there at the origin, so it's going to zoom in towards the origin. I'm going to hit enter, and there we've zoomed in on our function closer to the origin. Alright, now we found the equation for the tangent line at the point 1, 1. I'm going to go back to my y equals and also graph the tangent line that we found. So hit y equals, arrow down to y2, and I'm going to type in that equation we found, a negative 4x plus 5. So I'm also graphing the tangent line to the curve. So there's the tangent line, the equation we found, and notice how it is the tangent line at the point 1, 1. And I'm going to kind of highlight that point by going to second calc, and I'm going to enter the value x equal to 1. So there's the point 1, 1, where's where my cursor's at, and there's that tangent line to the curve. So that kind of gives you a visualization of the line that we just found.